Hello, everyone. Can you guys just clarify if everyone is able to hear me properly?
Yes.
Uh, oh, Thank you so much. Hello, I'm Charita. I'm actually a PhD student in Professor Srinivas Chakravarti sir's lab. Today, I would be doing the tutorial for the neuronal model you guys have gone through in the morning. Before even I get started on it, we have shared a Google Drive link via email, WhatsApp, and also on the chat box, which is the tutorial code link. Are you guys able to access the Drive folder? If not, please let us know immediately because those are the codes which you're going to run. Maybe not all of them, but definitely a few of the neuronal models you will be able to do the hands-on along with us. Okay.
Yeah,
Uh,
we
so
have received six folders.
yeah, so
And
we will be doing
yeah,
like three of them, whichever sir has covered. Remaining are for you guys to play around. Based on time, we can do more if it is needed. So I would suggest just download the folder and upload it into your own drive so that it's not running on other drives or any other people's, and you'll have the full access to the code. And also try running it on your Google Chrome because that will give lesser errors. Just try to make sure that you're putting it on Google Chrome and use it in your Google Drive. We'll be using them with Colab Notebooks. I'll just show you how it looks like once it is there. I'll just wait for a minute so that everyone joins and then start doing it. Uh, can you guys also confirm if you're able to see my shared screen? Okay, thank you so
Yes, ma'am.
much. Yeah, thank you so much. So you're also able to see the slides and stuff now, right? I mean, it's not
Yeah,
on
yeah.
full. Yeah, cool. So
yeah.
this is the folder we have shared with you guys. Workshop on brain modeling day one tutorials. Just download the entire folder and upload it off into your drive. Or you can make a copy of each of the notebooks separately. It's up to you guys, however you want to, but don't run the code in the same file. Just make a copy for yourself in your drives. I'll just wait for like 2, 3 minutes so that everyone is able to do that. Then I'll start with the tutorial part. We have to download and make a copy. Yeah, just you can download the folder here and upload it off into your drive. Starting. You guys will be starting by 2:06. Please make sure that you have set up all the folders properly into your drive. Make sure that you're on your Google Chrome, not any other ones.
Ma'am, do you mean Collab or VS Code? What do you mean by Chrome? I'm not understanding.
Oh, I said we'll be running it via Colab. Don't use other browsers like Mozilla or stuff. It's preferred that you use Chrome. I mean, you can still use it, but I think some kind of errors might pop up if you use it. We'll be doing it on Google Colab, not on VS Code.
Okay, ma'am. Thank you.
Yeah, sure. Can we start now?
Yeah, which is the file, first file we will be taking in? Kindly
Hodgkin-Huxley, HH model. The first file will be HH model. If you
HH.
want, just make a copy of that first. Yeah, so I'll just start for now. The first model we would be looking at is HH model. So the overall session will have this outline. Let me just go to the full screen. Yeah, so the overall session outline would be somewhere like this in a way. You'll be having first, we'll be doing the tutorial on Hodgkin-Huxley model. Then we'll go to leaky integrate fire, quadratic integrate fire, and Izikevich model. Maybe the last three models we will have like a little faster session, but Hodgkin-Huxley, you can have a proper time into simulating the code and looking through each of it. And for each of these models, we'll give you a quick recap of the neuronal equations that we are going to simulate and then go through the code and then let you guys simulate the code. Is that fine? Like, in a way, that's a plan for the next 2.5 hours. Good. So just starting with the Hodgkin-Huxley model. In the morning, I think you guys might have gone through the Hodgkin-Huxley model. It is one of the first neuronal models that was proposed. And the way they have proposed it is more or less using the circuit diagram in a way. That is, we model the entire membrane. The cell membrane in itself has a leaky capacitor. And then we also have different neuronal channels which are modeled using a battery as well as a resistor with certain amount of resistance or conductance. So this is what we technically have. First, the membrane as your capacitor circuit, and then we have sodium channels, potassium channels, and some kind of leaky channels. Okay, now the entire neuron is not as simple as a simple resistor and a capacitor kind of a combination. The reason is that the resistance or the conductance which are present at sodium and potassium are basically voltage dependent. You guys might have gone through it in the morning. That is, at certain voltage, these channels have higher conductance, and at certain voltage, the channels have very low conductance. That is, say, if my voltage has reached some 10 volts or something, the sodium channels suddenly open. So the conductance is very high at that point. At other voltages, they are not. So that is what we do. At the end of the day, we technically model the entire circuit. That is, I have an external current that goes in, will be equal to the current that flows through the capacitor, the current that flows through the sodium channels, the current that flows through the potassium channels, as well as leaky channels. That is what is technically written here. The total current will be your capacitor current, sodium, potassium, and leaky currents. Now, through each of these channels, what is the current that flows through? Like, few of the electrical engineers might be knowing that the current through a capacitor can be written as capacitance times dV by dt. Similarly, the current through different channels can technically be written as conductance times V minus the potential that is present here. So that is how we write it. But now, as I already mentioned, the sodium and potassium channels are technically dependent on voltage. When I say the channels are dependent on voltage, what is it that is exactly dependent on voltage? Any idea? Anyone? On the chat boxes, you can type. So basically, when we say, yeah, the conductance is actually what is changed. And the conductance change is because of the gates opening and closing. Think of it like a room ka gate or a door. It opens and closes based on the voltage. Now, these gates are what your M, N, and H. The dynamics or the opening and closing of this gate is what is controlled by voltage. Okay, so that is what we write. The conductance, whichever is there, is actually dependent on the gate opening or the closing. Whereas sodium channels have opening gates as well as closing gates. That is the reason we write conductance as a function of M and H. They are opening and closing gates of sodium. Similarly, conductance of potassium is also dependent on its gates, that is n to the power of 4. The powers 3, 1, and 4 are empirical. They have done some kind of experiments and did some kind of curve fitting to come up with these numbers. Okay. Now, as I already said, M, N, and H, all three of them are gates. all three gates, closing and opening, again depends on voltage. So again, they are also differential equations at the end of the day. So that is what I'll show you here. If you actually take the currents and substitute all the currents over here, this is what is the equation you will end up with. And you can take dV by dt to one side so that you'll have an entire differential equation for dV by dt. But what about M, N, and H? They are again gates which also have some kind of dynamics that is given by these three differential equations. Basically, alpha and beta determine their opening and closing, the fraction that is open and the fraction that is closed. This alpha, beta are the functions of voltage, and they have some constant function of voltage. Okay. So technically, that is what is your simple Hodgkin-Huxley model in a way, where you have a capacitor, sodium, potassium, and leaky potentials. And sodium and potassium channels are modeled using their gate dynamics. Gate opening and closing is a function of voltage, where alpha, beta are functions of voltage. Alpha M, alpha H, alpha N, they are actually some equations which are functions of voltage. Okay. So the first task for today is to try and understand the Hodgkin-Huxley model. How do we code it and what is the way we code it? Generally, differential equations can be solved using multiple methods like Euler equation or RK4 or even L-SODA models. But for simplicity and keeping it easier for everyone to understand, we will be solving it using a simple Euler equation. I'm sure you guys might have understood what is a simple Euler way to solve it. Say, for example, I have a differential equation as dy by dt, and I want to plot how does y vary with respect to time at the end of the day. This is how we compute it. Y at time step of k plus 1 will depend on y at time step k plus delta t, which you can fix what is the step size, into your dy by dt. This is how technically we do it. Say I have a dV by dt equation, right, in the previous page. That dV by dt is a function of voltage, M, N, H, whatever. For that to update it, I'll have a t plus 1th step. It will be tth step plus delta t times this function, dV by dt. Is that fine till here? Anyone has any queries you can go through now? Otherwise, I'll open the code block itself and show you how is it being modeled.
Hello.
Hello.
Yeah.
Like when we observe or like simulate this, what we are doing is basically like checking the gates if they are opening or closing.
Yeah, so for different currents, we will be testing whether the gates open or close and
Okay.
how does the voltage vary. So these are the simulations. Once I go through the code, maybe I'll show you what are the things we can check.
Oh, okay. Okay.
Yeah. Any other doubts? I guess someone else was having a query.
Yeah, so I just wanted to ask in the
Yeah.
previous equation,
Uh,
you were showing about those gates M, N, and H.
yeah.
Why M and H was in sodium and why only N was in potassium? Why
Uh,
all three gates were not together in that
s-
equation?
Here you meant? So
Yeah,
sodium
yes, yes, yeah.
channels, yeah. So sodium channels have their opening and closing gate. Now, when the opening
Mhm.
gate opens up, it implies there's a heavy flow of sodium ions. When the closing gate closes, it will be closed. Potassium has only one kind of a gate. So sodium currents will only depend on its gates, right? Which is M and H.
Okay, okay. So, like, all these three gates are not in the same channel. Yeah.
Yeah.
And
M and
okay,
H are sodium channel gates, whereas N is the potassium channel gate. I hope that
okay, okay, okay.
clarifies. Yeah.
Yes, 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 yes. Thank you.
Uh, s- okay, moving ahead, maybe I'll go through the code first and then I'll tell you what are the simulations that we are going to go through. Okay, first let's just look through the code and then get back here. Um, yeah, are you able to see my folder here?
Yes, ma'am.
Yeah, thank you. So once you open your HH model, there are three codes into it. One is the code Gradio and Solutions. First, I'll go through the code. Gradio code is actually made to be a platform. Whomever is not comfortable with the coding part, they can use Gradio. But I'll show both of them first, then I'll tell you however you want to do it. So just going through the code of the Hodgkin-Huxley, if you open your Colab notebook, this is how it's gonna look. Okay. The first code block is basically just importing all the necessary libraries for simulating the code. The second block is what is your overall Hodgkin-Huxley block. If you look at it, we wrote it in a class format, but you don't have to worry too much about it. The init function takes in all the parameters that I have to define. What are the parameters I need to define? If you actually look at your equations, you know that we need to define this GNA max, which is a constant, the conductance CM, which is a constant, ENA, EK, all these are constant values. So we need to define them. For you guys, we have already defined it in the code. These are some standard values which everyone tends to use. So we have defined all of them. GK max, GNA max, GL is the conductance of the leaky channels. These are the Nernst potential of sodium, potassium, and leaky channels when it's so EK, ENA, and EL. And C is the membrane conductance. Then we also initialize certain kind of monitors so that we can keep monitoring the voltage with respect to time, conductance with respect to time, and the gate parameters, how are they varying with respect to time. Then what is DT and ITER? If you remember, DT is because of your Euler equation. To solve any differential equation, we need to define some kind of a step size. It generally tends to be between 0 to 0.1. 0.1 is the max people tend to use. Beyond that, you will have a lot of error in calculation. Numerical error, I meant. So we tend to take either 0.1, 0.01 based on the precision we need. So I think for this code, we tend to keep it at 0.01 if I'm not wrong. Now, here is the function solve. This is the main function which actually takes in and solves your differential equation. It takes applied current, which is your external current. In your differential equation, you actually have an external current, right? This is what we
Sorry,
are going to
ma'am.
play around with. Yeah.
Sorry, ma'am, to interrupt.
Yeah.
You spoke. What is the iteration we are like mentioning there? You
So
said DT is for to do differential equation, and we have set to 0.01.
Yeah.
And what is iteration? Where do we define any specific iterations, or what is the impact of that definition?
So when I have to simulate a neuron model, I have to simulate it for certain time, right? I can simulate it for 1 second or 10 milliseconds or 100 milliseconds, right? So I
Okay.
have to define how many iterations I have to see. Like if I have a step size of 0.01 millisecond, and if I simulate it for 10,000 times, it implies it is 10,000 times 0.1, right? Which will give me like 1,000 milliseconds.
Okay, got it.
So it'll define a time, overall time, how much I'll simulate it for.
Yeah, I got it.
Yeah.
Thank you.
Then going through the solve function, we have an external current. If you remember it very clearly in your differential equation, we have an external current that has to be applied. So that is what the function actually takes in as an input and solves for all your parameters. That is, it will solve for how does the voltage look like, how does your conductances vary, and how does your gating parameters change. So these are the initial conditions. See, whenever I need to simulate a differential equation, I need to start somewhere, right? That I have a resting membrane potential, that is where I'm starting from. So these are the initial conditions I have. And then we will start simulating our loop. Why loop? Because I have to simulate it for multiple time points at 0.01 milliseconds, 0.02 milliseconds, and stuff. It will run it. So I'm going to define all the things here. I'm having GNA, that is the overall conductance of sodium, is GNA max times M cube times H. Where do I get it from? From here. If you look at it, all these three together is the overall conductance of sodium, right? GNA max is a constant. The product of all these three terms is sodium conductance. That is what is written here. Similarly, for potassium conductance, it is GK max times n to the power of 4. That is what you have it here. Okay. Now, after that, now I have to compute your voltage with respect to time. Can you see and the equation highlighted? Can you identify it's your Euler update? That is, v at next time point is updated as v as previous time point plus dt times whatever your differential is, right? So that differential is basically this. If you look at it, it's your differential. Is that okay for everyone? Where did I get dV from? It's actually here. dV will be equal to all these conductances sums minus the external current divided by capacitance. That is what is basically, we wrote it here. We define dV, then we define V is equal to V plus dt times dV. Okay. Now, this is for your voltage.
These
Yeah.
equations are okay, but above actually M, H, N, V, initially, like from where did you get it? Because earlier in the earlier block, you said that those are the constants, correct? This is fine,
I
but
said GNA max, GK max are constants. In this, what are the variables I have? The variables I have are voltage, M, N, and H are variables, right? Technically, because
okay,
they vary over time. Now,
okay,
to simulate any Euler equation or any differential equation, I need initial condition, right? See, the next state update depends on my previous state. That is, at t plus 1, I depend on t. So I
yeah,
have to start somewhere. So
yeah,
I'll say initially this is the condition I have. So what is the next step? That is how Euler runs.
okay.
So when I wrote this, I'm saying these are my initial conditions because
No,
minus
my
65 is
question
somewhere.
is, do we
Yeah.
take it as random, or you had completed some exercise and from there you're starting this? That is my question.
Yeah. So voltage is technically always taken at resting membrane, closer to resting membrane. And the others, we took it from some kind of resources. So these are more reliable like that.
Okay, ma'am. Thank you.
Yeah. Thank you. So once after voltage equation is defined, we also need to have a differential equation solving for M, N, and H. So you can see that this is the Euler update, and these are your differential equations. Right? dm by dt is alpha m times 1 minus m minus beta m into m. Now, as I already mentioned, your alpha m, alpha h, alpha n, beta m, and beta h are functions of voltage, and they are constant equations. These are the equations. In the material we are going to provide, we will give you with all these equations. You can have a look at it as well. These are simple standard equations, some non-linear equations. It's like 0.1 times v plus 40 divided by 1 minus e power v plus 40, something like that. So we just solve all these things and just append it into a monitor so that we can keep a track of it over time. Is the entire running loop clear? Because this is how we are going to write code for all the other neuron models as well. We'll always have these dm, dv, whatever variables I have, and then update it using Euler. That's all we do. And we'll just return that from the function. You can run it on your code blocks as well.
I just wanted to ask one more question.
Yeah, go ahead.
Yeah, so I just wanted to ask that when we do that work independently, then do we have to write code from scratch, or do we have some sort of template to work on it? Like you
We
are
gave you
showing
the
me.
code, right? For now, we all want you is to just run the code we have given. That's all. That's the reason we asked you to make a copy on your Google Colab so that you can just run the code and have an experience of the model itself. Then you can sit down, think about how to write a code of it and stuff. I mean, generally, these codes are available everywhere, so you can always pick the code and run the model.
Okay.
Yeah.
Yeah. And one more question is
Yeah.
that I'm very new to coding. So what does the self-dot function do? Like when we add this thing, self-dot, what does this function do? I just wanted to know
Oh,
that.
this one. So whenever we
Yeah.
write everything in a class, so this
Mhm.
class will have some kind of global variables and few variables which are only specific to these functions. When I declare it as a self dot variable, it becomes a global variable and I can access it anywhere
Okay.
within any function. Like M here, it doesn't have self dot, right? So it can't be accessed outside the function. It has to be accessed only within the function. When you have self
Okay.
dot, I can access it from anywhere.
Okay. Yeah. Thank you.
Yeah, sure. So I hope all of you guys have started opening your code notebook and started simulating it. If not, kindly open your Colab notebook of hhmodel_code and you can have a look at it. Cool. That's great. Uh, Please let us know on chat box if you guys are facing any issues or anything so that other people can handle it in meanwhile. Okay. Yeah, so that gets us to the code part. Now we have to simulate it for whatever iters we want and stuff. So you see this, I have initialized my class. All the classes have to be initialized, which takes an input as
Ma'am,
DT
I
and
have a
iter.
question. Sorry, ma'am.
Yeah,
Sorry to interrupt.
no problem.
In that code block, you're returning self, correct? And it is getting appended in a list, correct?
Yeah.
Will you be able to print one value and see? Like, I just want to see what is the value which is getting into the list.
Yeah, so
I'm not
once
able
you
to print
run
it.
it here, you can see it. You see these, right? These are actually like what you have. And if you want to actually print at each time point, you can add a print statement here. Just do print of M, whatever
Okay.
variable you want to print, it
Yeah.
will start
Okay.
printing it.
Got it. Got it. Got
Anyway,
it.
since it returns all the things in an
Okay. In
entire
a single,
list,
after completing the iteration, it is giving us a final output, correct?
yeah. So
Yeah.
here, all these things, whichever are there, they are being returned.
Okay. Fine.
Yeah. So first thing is we are actually initializing your Hodgkin-Huxley model, and then I'm going to solve it for different currents. So now what we want you to do is try out for different currents and see how it looks. Okay. But before that, I'm sure few of you guys are not very familiar with coding. How many of you are not really familiar? Okay, a few of you guys, right? So for you guys, what we have done is we have another file inside the code block, inside your folder called HH model Gradio. Can you guys open that code block? Kindly open it on your Colab notebook only on Google Chrome. _Gradio. The code is for people whoever are able to understand the code. Otherwise, there is an interface where you can just change the parameters and run the codes. In this, you don't have to do anything. Just run all the code blocks. Yeah, in this Gradio code, if you guys are opened, just run all the code blocks. Once it runs, it actually launches a link. Okay, just it's taking a little while to execute. Guys, this is for people who are not very familiar with coding. You guys can run the Gradio code blocks. Just run it till the end. It will generate a localhost link. Just click on that link and open this page. It will open a browser page. In this, you can experiment. The way you're going to experiment is just enter whatever external current you want to enter. That is, say I want to enter 0 as my external current. You can keep the duration and time steps constant because that is how you're going to run the total time and time step. You can visualize all the variables whichever are needed here. You can tick on them and just click on run simulation. It will run the simulation and generate plots. But try to make sure that you're running it on your Google Chrome, not otherwhere. Otherwise, it will throw errors. For whoever are comfortable with code, you can actually go here and change your applied current here and run the code. Is everyone set with the code blocks? Either you guys follow Gradio or you guys can follow the code, whichever is comfortable for you guys. So that I'll tell you what are the things you can visualize and you can run and see for yourself on hands-on. We'll give you like 5 minutes for that. Any doubts still here?
Yeah, actually, hello, ma'am.
Yes, Abdul.
Yeah, we are getting the output right below it, right? The white graphs.
In
This
the
is the
code
output, right?
one, yeah.
Yeah,
I'll tell you
yeah.
what all you can change and modify so that you can look at what you have to do.
Mm-hmm.
Yeah, I'm just waiting for people to run all their code blocks so that I'll tell what is the experiments that you guys are gonna do.
Okay.
Okay, I'm assuming everyone is set now. So the sole goal of this part of the simulation is this. First thing is, I'm sure you guys would have seen that in your,
Sorry, ma'am. Give one
sorry.
more minute, please. Give
Yeah,
one
sure,
more minute.
sure. Yeah, sure. Okay, maybe when we'll wait for 2 more minutes and then start. Guys, can you also respond on the chat box if you guys are set up with the code done? Either the code version or the Gradio version, anything works. Thank you so much.
In the Gradio version, hyperlink is not working.
When you run the where are you simulating the entire code on? I mean, in Chrome or somewhere else?
Firefox.
Can you do it on Chrome? Firefox will have some local host error.
Okay.
Yeah, that is why we were asking people to run it on Chrome. If you run it on Chrome, it'll be fine. Just log into your Google Gmail and then run it.
Okay, ma'am. Thank you.
Or you might also have a inbuilt inline block looking like this instead of the link. If that comes up, you can run it here also, if that works. But Chrome is safe side, just letting you know.
Yeah, it is there. It is been working in the collab section only.
Yeah, if it
It
works
is
for you, then it's fine. If it works within the Colab itself, then also it's fine. I'm sure you can run it here also and visualize it. Okay. So guys, just letting you know what are the experiments you guys are going to do. Just focus a little here. The first thing you guys are going to observe is as you change your external current from 0 to some 0.6, 0.7, where do you actually see an action potential? That would be your first question to answer. Along with that, also visualize membrane conductance. How is it varying? And how are the gate variables actually varying? For people who are using Gradio, it's very straightforward. There is an applied current region where you just have to apply smaller currents like 0.01, take all the variables and run the simulations. And for people who are actually using the code block, there is this I applied here. You can apply current there and then do the simulations. All we want from you guys is to type on the chat box. You keep adding the different currents like 0.0, 0.1, 0.2, 0.3 till some 0.6 and let us know where is it that you're actually seeing action potentials. That is your first task. Maybe you can type on chat boxes once you get the results. The currents can be tried between 0 to 0.6.
So once we run the simulation, what is the value you want us to type as, please? Type.
So when you do it for different currents, like I ran it for 0.0, then I can run it for 0.1, then I can run it for 0.2. There'll be a point from which you will actually start seeing action potentials. Maybe initially you won't see an action potential. You just want to know that approximate current which you are observing.
You mean gating variables and ion channel conductance for 0.1? I'm not seeing anything. So you want me to go for the next value
Yeah,
while the
just slowly increase it. Yeah, just increase it to 0.2, 0.3, and so on, and see where it works.
Okay, 1 minute, please.
Yeah, sure. Kindly, everyone, you can also have a hands on that so that you'll understand how current will influence your action potentials.
Ma'am, what do you specifically mean by action potential, ma'am? Can you just put 0.1 and show us, because I'm seeing membrane voltage is present, gating variables are present, ion channel conductances are present. So what is it you are specifically?
So you'll see such spikes continuously
Yeah, that's right.
for certain value.
That's right.
Yeah. Where do you see such a change?
Change. Okay.
Yeah. Maybe not 0.03, it will be slightly higher, or even 0.05. Okay, let's see. Yeah.
Yeah, I just wanted to ask one more thing. When
Yeah.
you say that when it's the first time we see like changing value, the action potential. So like, is it when you see the first action potential? Because I have just changed the value and I'm just seeing the only one action potential. So does it count, or you want me to do it like
Yeah, that is also
as
fine.
it's
That is also fine. Single action potential also should be okay.
okay, so it's showing on the value 0.023.
Okay.
Okay.
I'll also simulate. Oh yeah, I think everyone are right. 0.04, 0.06. Yeah. Okay, then maybe I will also do the simulation with you guys so that you can also visualize what people are actually seeing through. So when you actually have a current of 0.0, there won't be any voltage change per se or any gating variable changes you would actually see. Even if you apply like 0.02 current, here also you won't actually see an action potential. Action potential, the voltage actually goes to a positive value and then only comes down. Like it'll reach some 30, 40. Then only we call it as an action potential. So this is not actually an action potential. We'll further increase it slightly to maybe 0.023. Yeah. Now can you guys see first action potential? That is, it shows a positive peak. It reads some plus 25, plus 30 voltage. And you can actually see the gating variables and also conductances. People using radio can also simulate it here. You can use 0.023. You'll see voltage, gating variables, and also ion channels. Is everyone able to simulate it for that number? 0.023. I'm assuming yes. Okay, so what I want you guys to clearly see here is M is the opening channel for sodium. You see, as the voltage keeps increasing, the M channel the M channel value increases. It implies it suddenly opened. Can you observe that? And slowly
Yes,
the
ma'am.
closing channels open. That is, first the sodium channels open, because of which this M is like suddenly peaked. Then it closes and the closing channels also start to close. After the M channels open, then only you will see the N variability. N is basically potassium channels. And potassium channels are the reason why the action potential decreases. I'm sure you guys might have remembered that, right? Why opening potassium channels will decrease the voltage while sodium channels will increase? Anyone?
Because it hyperpolarizes, you know.
Yeah, so when sodium channels are open, the gradient or the concentration gradients are in such a way that sodium ions will enter the neuron. So the voltage increases. Whereas when potassium channels open, potassium ions move out of the neuron. So the voltage decreases. Is that okay till here? Are you able to understand the voltage and gating variables pattern?
It's like the resting membrane potential will be at minus 70. Then due to
Yeah.
depolarization, it will increase to plus 20 millivolt, and finally it will get back to the resting membrane potential, right?
Yes. But
Okay.
the increase is basically because of your sodium channels opening.
Okay.
And the decrease comes because of potassium channels opening.
Got it.
So the way action potential works is first sodium channels open and then potassium channels open.
Okay.
And potassium channels are open for a little longer time. It takes a while to close them. So that is why you will see that hyperpolarization. That is, the potential actually goes below its resting membrane and then enters resting membrane. Now, going through the conductances, you will also see very similar pattern. You see that the potassium conductance spikes very fast and falls very, very fast. But whereas potassium conductance slowly raises, by the time sodium is falling down, potassium raises, and then it slowly falls down. About gating variables once. So gating variables, we have 3, right? In that, N is the potassium gating variable, M and H are for sodium. M is opening gate. That is, as the potential increases, opening gates of sodium increase. I mean, open, basically. So the M value actually raises. Once it reaches its highest value, its closing potential or the closing gate will start opening. That is the reason you will see a dip. Once these happen, then only the potassium channel N opens. So you'll see a slight delay in the peaking of both of them. Is that okay? Does that answer your question?
Yes, ma'am.
Yeah, thank you. So this is what we want you to observe on first action potential at 0.023. Now you slowly increase it a little bit more to 0.06. Probably you'll see some 2 action potentials. You further increase the current. Say I'm going to increase it to some 0.065 or something. You'll see a continuous firing. Okay. And here also the voltage reaches pretty high values. And again, you'll see the conductance variability as well as gating variables. Now, what happens if I keep increasing the current very, very high? Did anyone try out very high currents like 0.6, 0.7? Let's see what happens. Yeah, if I give it to 0.6, do you see there is a first peak which entered into positive regime or greater than some 20 volts or 20 millivolts or something? All the other peaks are actually kind of distorted. Can you see that? They're almost zero. They are not technically action potentials. Action potentials are always considered to be above 10 millivolts. If it reaches about 10 millivolts, then only we can treat it as an action potential. 10 to 20. I mean, few literature suggests it's 10, few suggest it's from 20 to 30. That is okay, but the zero is definitely not treated as an action potential. This is what we call it as distortion. Any idea or any guess why it might happen? Like I increase it further, it will be even more distorted. Like if my applied currents are 1, it will be like almost minus 25. It doesn't make any sense. Any idea why this might happen? If I keep increasing current so high, why is there no action potential? Yeah, the amplitude decreases. That's what I meant. Any guesses why the amplitude decreases?
Because of refractory period?
Not exactly like that, but you're kind of right there. See, whenever I have high currents, the gates have to open and close. There is a limit to it. I can't keep doing it very fast. If I keep doing it very, very fast, do you think ions will have enough time to enter and move out? Because ions entering and moving out is what is creating your action potential or the voltage change. If I keep closing it very, very fast, they won't have enough time to rush inside or outside. So that doesn't change voltage a lot. That is the reason after certain currents, you will start seeing distortions of action potential. Does that make sense?
Yes, ma'am. Yes, ma'am.
Yes. Good. So this is the trend you will actually see. For very low currents, there would be minor change in voltage, but there won't be any action potential. For moderate current, you would be seeing action potentials. For very high currents, you'll see distortion. Okay. Even during moderate current, if I increase currents, any guess what might happen? The frequency of action potentials increase. Is that okay? Action potential amplitude will never have a change. It's only the frequency at which it changes. Like when you tried it out at 0.023, it was only one action potential. Then around 0.06 or something, you had two. Then further increasing, you will have more action potentials. Further increasing, it will increase the frequency of action potentials or number of action potentials in a given time point. Is it okay for everyone?
Yes, ma'am.
Yes,
Okay.
ma'am.
Yes, ma'am.
Okay, so with this kind of a background, we want you guys to do a small task. We will give you out the code later, but we want you guys, what we'll do is we will split you into a couple of groups and we will allot you guys into separate rooms. We want at least one person in the group to share the screen and try coding for the further part. We'll explain what is the task and what is it expected. Is that okay? We'll tell you where the solution is also, so you don't have to worry so much about it. If you can't also, it's totally fine. We'll give you the solutions to it. Okay, so going ahead, the task would be to compute frequency for each external current. Right now, we have tried out at each of the external currents, right? That is, I have tried it out at some zero thing where you actually don't see any action potential. Then you also tried it at some 0.2 or something or 0.1 or something where you actually see some kind of action potentials, right? Now, what we want is for each of these external currents, like 0, 0.01, 0.02, or 0.001 and stuff, what is the frequency? By frequency, what I mean is what is the firing rate or number of action potentials? That is, when I have it at 0.1, can you see this the number of action potentials for a given 100 milliseconds time? I have 1, 2, 3, 4, 5, 6, 7 action potentials, right? That is for 100 milliseconds. When I say frequency, I need it for 1 second. That is 1000 milliseconds. What will be the frequency? For 100, we have 7. For 1000, it will be 70 hertz or 70 action potentials. So we want you to plot that. Let me show you on slides what is exactly expected out of you guys. This is what we want. See, when you want for each of the external currents, you'll have certain number of peaks that are present, right? You have to count how many peaks are there for each of the current and plot a frequency curve. It kinds of looks like this. I have an external current and a frequency. You'll see that initial currents for 0 to some 0.05 or 0.06, you won't have any action potentials. After that, it suddenly increases. After some time, you will have a distortion. We want you guys to try and plot this. Okay. Is the task clear to all of you?
Yes, ma'am.
Okay, cool. So I'll tell you guys before itself, there is a solution code blocks which is present in that solutions. If you want, you can refer to that as well. But all we want is once we make you guys into groups, we want you to discuss whatever we have done till now, look through the solution, understand how are we plotting this frequency and discuss why is the frequency like this. Is that okay? We'll give you kind of 20 minutes and we will move around the rooms so that you'll have a clarity of what is going on. Is that fine, everyone? If that is fine, then maybe we'll start making breakout rooms for you guys.
I'm sorry, my signal might have broken. Am I
Yeah.
audible?
Yes,
Yeah,
Varnika.
I missed the part where you were asking what exactly to do. Sorry, can you repeat?
So we will be creating breakout rooms now and we'll be giving you 20 minutes. Okay. We want you to discuss whatever you guys have done till now, whatever you have understood. And the next thing we want you to do is this frequency plot analysis. Okay. We want you to write the code for that frequency part. and analyze for different currents how is the frequency looking like. For that, you already have code in the solutions notebook. You can run that solutions notebook directly if you want to. If you guys have no idea about coding, just run it till the end. It will give you the plot, but understand what you guys have done till now. Is that okay?
Yeah,
And we will
got
be
it.
coming around the breakout rooms to clarify. Like it's some 2:50 now. You can
Uh,
do the activity till some 3:10, maybe 20 minutes. This is
Hello.
mainly for interacting and stuff.
Cool, got it.
Yeah. Someone was asking something?
Yeah, actually, this is a published work. Am I right?
Yeah, Hodgkin Huxley is a published work long time, so it's a very available
Uh,
code.
I think which journal this work is published?
I don't know. It's some 1960 to 70 publications, so I don't remember where they published.
Oh, okay.
Yeah, it's a very, very old and a very classic neuron model for everyone.
Okay, great.
Yeah, so we'll be creating the breakout rooms now and we'll be giving 20 minutes. Yeah, create the breakout rooms. I guess you guys have gotten some invite for joining the breakout rooms. Can you please join your breakout rooms and start discussing? We will be moving around. Guys, whoever are outside the breakout rooms, you can join your breakout rooms for discussion. This is just for interaction and having a conversation with your peers. We will be coming through the breakout rooms to explain you guys further processes if we're needed. Hello. Am I audible to everyone in the breakout room? Can someone respond? Okay. I want one representative in the group who can actually share the screen and run the frequency code. It's okay if you guys don't really know the coding. That's okay. You already have a solutions notebook. You can just share the screen, run it, and just discuss among yourself. I would prefer people unmuting themselves and having a conversation. Yeah? Can someone? Krishna, can you unmute yourself for discussion? Oh, come on, guys. You guys are only gonna discuss. Nothing is gonna happen over it. Can someone unmute yourself?
Yeah.
One second. Someone unmuted. Oh, thank you so much, Krishna. I was asking if you can take charge here, just sharing your screen and running that student notebook version and showing how the frequency looks, and you guys can discuss among yourself. You'll have
Actually, ma'am, I'm opening this in a tab. Is it not a possible in tab?
oh, okay. Anyone else who is there? Niveta, Lakshmi, Angel. Otherwise, you guys are gonna sit here for another 10-15 minutes without doing anything. Why don't you guys do something then? Or at least have a conversation about what you guys have learned till now. Yes, Angel. Can you at least unmute yourself once? Okay, sure. Maybe you can run the code and have a conversation on the chat box if you guys are comfortable like that. That's also totally fine. If that is the case, I'll go have a look at other people as well. Yeah. Can you open the student notebook version that will actually have your frequency code? Yeah. So just run it and see how the voltage, I mean, how the frequency versus the current plot looks like. And you guys can have a chat on the chat box itself. Okay. Okay. Then I'll just go through the other breakout rooms and we'll be back here in a while. Hello, guys. Is there anyone who's sharing their screen and trying to discuss stuff here? Any volunteers at least?
Yeah, we were just introducing each other. Yeah.
Oh, okay, no problem. Maybe then I would suggest you introduce yourselves, have a conversation about what all you have understood on Hodgkin-Huxley, and you can run that student version code book because since we don't have enough time to actually sit down write code, you can run that student version code book with only like 2 boxes that are different in that, and you can understand the voltage, I mean, current versus frequency plot. Will you guys be able to do that?
Yeah. Which code again? Sorry.
Uh,
We'll try like
Yeah. So when you open that Hodgkin-Huxley folder, there is a
Yeah.
solution book, right? That's
Okay.
basically the code book itself with extra added code for your task. Thank you, Ashwin. I think
Thank you.
Ashwin has already, yeah, you just have to plot it and see how it looks
Yeah.
for now. And have a conversation on why, how, and kinds of stuff, whatever you want to discuss.
is my screen is visible and
Yes,
shared.
Ashwin, it is. Yeah.
Okay, this is what you are supposed to run, right? This
Yeah, this
frequency.
is what I meant. Yeah, so you can understand why, right? You might have done each and every current experiment on the top, so you'll understand why the frequency should look like this.
Yes,
And
yes.
you can understand the code block as well. I mean, you guys can discuss over the code block and have a conversation. Okay, cool. Then I'll go to the other breakout room and check out people. All the best.
Thank you.
You don't have to
Thank
fear
you.
out on discussing. There's no one here, so you guys can discuss whatever you want to freely.
Whatever the solution was there and discuss about that.
So are you able to run the given code? Like, are you able to set it up and run?
I can't see who is speaking. Okay, Angel, are you speaking? I think,
Hanika.
okay. I think for running there is a small triangle on the left hand side corner.
Yeah. So
You
I'm asking, like, have
uh,
you run the code? Question part have you run?
I mean, yeah, what she was teaching that I have run, but again, for Python, this is my first interaction with Python as well.
Okay, frequency versus that section and showing me some sort of loading or something like to
Okay.
plot it.
Abhin, you have shared your screen.
Yeah.
Yeah, would you be able to brief anything?
Yes, and the code and code is now.
This is that solution one, right?
Yeah,
Jo. Okay,
this
okay.
is solution. I think it's a frequency curve. We are plotting the frequency and the input current. You can see the zero level.
I'm not able to hear clearly what you're saying. Does anybody else is able to hear him, or is it a problem on my end?
Can you hear me now? Hello?
This meeting is being recorded.
Our firing frequency will increase to the point when a threshold value of current is being reached, right?
Yes,
And
yes.
then after certain value of current, we won't be able to see firing as much. Is that what it is saying?
Yes, I think that is the
And
summary.
okay, okay, okay.
I think there are three levels of current cases in this plot: low, medium, and high.
Okay.
She told this earlier.
Okay, okay. And do we have any term for this threshold value when we are not able to see any firing frequency where it is dropping, like around 0.68 or something?
Yes, yes. From 0.02 something 0.05 maybe. That
Do we
within that range there is no firing.
right, okay.
That is the reason the frequency is zero in this period. You can see means there is no peak within this period, and after this current voltage, so you can see the increasing of the frequency.
Acha, right. Okay, so I guess this is what it is, right? I mean, do we have anything else to discuss around it? Guys, please,
Hello,
please,
guys.
you cannot be more dumb than me. Please just say anything.
Hello, guys. I
Hi.
am just here. I just thought I'll have a look through if you guys have any queries you guys want to know.
We actually, Abhin, can you please show that graph? Yeah, actually, we just ran this, this session by ourselves, and we are very amateur here. So we were just discussing
No
what is
problem.
happening in this graph. So
Yeah.
as we gradually increase the current and frequency of firing will increase with it. But
Yes.
at a point, that firing drops, very abruptly. So we
Yeah.
were just discussing around that.
Oh, okay. So basically, when there are very low currents, you guys understand that it might not have reached the proper potential voltage such that the sodium channels can open. That is in your initial range where there is no action potential. Once the action potential starts, as you keep increasing the current, the frequency increases. But if you increase it beyond a point, what happens is the gates are opening very fast. So it doesn't have enough time to exchange the ions. So it doesn't actually result in action potential. If you actually go up into your previous code, I don't know who is sharing it. Yeah, here, in this, can you change your external current once? Can you go a little up? I think I applied, right? Yeah, you have it at 0.47. Just give it as some 0.1 first. Yeah, just run it. I think I should have asked you guys to. Yeah. Now you see that if you actually have a look at it, the maximum voltage might have been beyond 10 or something. That is the highest peak point where it reaches is somewhere beyond 10. Beyond 10 is what we actually consider it as action potential. Otherwise, it's not really action potential, but merely a change in voltage. Few people also consider it as N. Few people also consider it as some 20. Few people also consider it as 30. It's up to you where you want to keep the threshold to be. But beyond certain point, you actually don't reach that full length action potential. So we call it as distortion. That sudden drop in the frequency is because of that distortion, that it won't reach certain potential. Like you increase the total applied current to some 2 or 10, maybe. You'll see more better distortion. Sorry for that. Yeah. Maybe like 10. No, not 0.2. Maybe like more than 1. 5 or something. You can see more better distortion. Yeah, probably it should work. Yeah. Yeah, now you see it's like completely nullified. There is nothing that you see. So that is what happens if you keep increasing current beyond a point. So you will see a sudden dip in that frequency. Does that answer your questions though?
Yeah.
Okay.
Do we need to discuss anything else apart from this?
No, I just wanted to check what you guys were discussing. I'll also go to the other breakout room. Maybe in 5 minutes, we'll break out of these rooms and get back to the main
One
session.
question.
Yes,
Excuse me.
Vanika.
Hey.
Yeah.
Yeah, so there is this slide in the plotting frequency versus external current section where you are giving an array of external currents. So
Yeah.
what does that mean? Like with respect to time, you are passing the array of currents value, like
No.
how does
If
it
you
work?
actually go a little up, for each current, I'm running your previous code. You see that previous code where we ran that hh.solve, right? For each of the current, I'm going to run that. Can you go to the above code block a little bit about that? A code block above this. No. Just in that frequency itself, one where you had the just a little down. Yeah, you see this for loop wherever I'm starting. I have a Hodgkin-Huxley model that is initialized. I'm solving it for that one specific current. Say it's 0 first, then it will solve for 0.1, then it solves for 0.2, then I'll count the frequency. So for each of the current, I'm running your previous code fully for all 1 second and then compute the frequency. Yeah.
So we can change these values and check.
Yeah, like IEXT, I have given only in between 0 to 0.7. You can increase it further to some 10 and stuff and see whatever you want to see.
Okay.
Yeah,
Okay, cool. Thank you.
cool. Thank you. Hello guys, I'm just visiting to check if everything is fine for you guys.
Yeah, yes. I just actually went through the model solution you provided in case
Okay.
somebody did not get it. So, but
Yeah.
someone had a question regarding the application of this. Maybe you might be a better person to answer it. I don't know who it was.
Okay. So the thing is, we no longer use single neuron models anywhere. We tend to model cluster of neurons because most of the times it's the cluster of neurons which is actually gonna be like having a change. Like say if I want to model some kind of a Parkinsonian phenomenon, how the neurons behave, it'll be definitely a cluster of neurons together show such a behavior, right? So we can model cluster of neurons like that. It won't be a single neuron. Then we can actually see what frequency, how does the neurons behave for medication and stuff. Those are
But
extensions to it. We are not
but
doing it right now in this.
sorry, but beyond a point, just using individual. So this same equations across a lot of does it work beyond a number of neurons?
It should work, but it's computationally very intensive. That is the reason you actually saw simple neurons today. Like there are 2 variable neurons, 1 variable neurons, which are very equally as strong as Hodgkin-Huxley model, but computationally efficient then.
Okay, and so with these I am very new to this
No
neuron
problem.
level models. So with Hodgkin-Huxley models of single neuron or two neuron, like double variable models, do they actually simulate layers and stuff? Is that possible?
Yeah, it is possible. So I don't know which project you guys are in, but there's one project which I would be dealing with for Parkinson's disease and STNGP and DBS model. You'll actually see a network of spiking neurons and how are they influencing Parkinsonian behavior and how does the DBS influence them. So you'll actually see those things when you look through the projects.
Okay, thank you.
Yeah.
And one more final question. So the
Yeah.
10 millivolt threshold, how do you choose that? Why did you choose?
So they are empirical. It's up to you. Anything beyond 0 is not treated, below 0 is not treated as action potential. It's a coding convenience. People certain times keep it to 30, sometimes keep it to 10.
Okay. So
Yeah.
because I used a different value and I ended up having a different answer. That's why.
Yeah, that should be fine. I mean, it's based on what you want to consider as a threshold.
Okay, so does this threshold change by the area in the brain, like the neurons belonging to, or
Probably different. Yeah, probably different neurons. We treat action potential slightly differently, but the threshold can be around 10. In general, that's how everyone keep it around 10 to 20.
Okay, thank you.
Yeah. Okay. Maybe we'll be like leaving all the breakout rooms. We'll be closing it in like 2-3 minutes. You guys can go back to the main session then. Hello everyone. Are you guys back here? I'm so sorry for abruptly closing up in between your discussions, just not to overshoot our overtime.
No
So were you
problem.
guys able to discuss within your breakout rooms regarding the frequency curve and anything regarding the action potentials on Hodgkin-Huxley and stuff?
We copied the three models from the model blocks, three blocks, and we put it in our first code, and we ran it, and we got the output, and also we try to understand where the noise is being manifested, and what we
What
could
do you mean
see.
by noise?
Noise means see, even after increasing your external current, there is no significant action potential, or it is a flat.
Yes.
The distortion he mean, the distortion.
Oh, okay.
Distortion.
Yeah, I
Okay.
understood. Sorry. Yeah,
So
got
some
it.
like even though we are not able to achieve the numbers, but graphically we are able to show that somewhere around 0.48 or 0.49 from the peak of 110 hertz, it is drastically dropping, and after that there is no activity. This is what this graph could show us. But you had specifically asked how many action potentials are there. That print command we tried to do, but in the first block of the code there was peaks. That is location of peaks in the given voltage. There we got, when we printed peaks, we got 82, but we are not able to correlate with the achieved graph. Okay, and when we try to print frequency, it was saying 1.0. That also we are not able to understand. And also we wanted to break down the x-axis and y-axis to a smaller value, so that we clearly understand at 4.9 or 110 hertz it is breaking. That is breaking of the x-axis to y-axis to lesser scale we were not able to do. And one more thing we try to print is the frequency monitor, that is FREQ underscore monitor, and I external, that is the external current. But we got array value. At least this external current we could understand it was starting from 0 to it went up to 0.7, because our PLT figure we have kept it as 10,6, so it went up to 0.0 to 0.7. But in case of frequency monitor, it is starting from 0 dot up to 1 dot, which this particular array we were not able to understand. So basically what we try to do is copy the code from the model and put it into from the solutions and put it into the model and run it, and we increase the PLT figure size. We try to make it bigger to understand at where it is breaking and what is the corresponding frequency in hertz. That is what we did.
Okay, so to clarify one query which you asked to the end, I'm just running it. I'll just let it finish first. So when you actually print IEXT and frequency monitor, you have IEXT values, right? 50 numbers, you'll have 0, some 0.1 EXT or 0.2 EXT till 0.7. So each of the index are correlated. For a IEXT of 0, the frequency monitor of 0 tells for that external current what is the frequency.
Oh, okay.
Yeah, I'll maybe plot it. Just 1 second. It's almost done.
So I have achieved a maximum of 115 frequency.
Yeah.
Is that the number?
Yeah, so you basically see this. You have a IEXT of 0, right? The external current is 0.0. For that, the frequency is 0. Say IEXT of 1, frequency of 1, if I put it. The second, wait, what happened to it? Did I round it up? Okay, IEXT of some 10. Yeah, 10 has a current of 0.14 or whatever, right? Similarly, frequency monitor of 10 would actually tell you what is the frequency of that. So for this specific current, this is the frequency. You understand the correlation. It's the index.
Okay.
I understand,
Yeah.
ma'am. So if it around like 0.48, what would be the frequency, ma'am?
So I think we have to check at what range of IEXT it will reach to that current. Let me plot it and see. This is 0.4, right? 0.28 current, it is some 98. Say I plot at 30. The external current of 0.42 has 112. Similarly, maybe 35. Yeah, current of 0.45 is now having a frequency of just 2 hertz. Just you have to print all of them. Maybe in a for loop, I can print and show. For I in yeah. I'm just trying to print whatever you guys asked for. Yeah, now you see it. You have for each of the external currents, what is the frequency it has plotted. So you can see that after 0.4571, I had at 0.471, which is where your frequency suddenly dipped to 4, and further it just fell off. I hope that answers a couple of questions.
Yes, ma'am. We've tried to print it, but maybe we should have done it in for loop.
That's okay. Since they are arrays, that's how we have wrote the code. So that should be fine.
But I'm okay with this 115, but it did not happen at the external current of 0.457. It happened at around 0.47 or 48. Can you show that graph, please? No, I understand that. This is so can you just make it no niche one.
Yeah, here.
That graph output matplotlib.
This graph.
Yeah, hold it. So here, can you make it like the
Bigger
size
one,
of
you
this,
mean?
the size to be 10,6 or 10,7, whatever it is. Yeah, run it, please.
Yeah.
Okay. So, okay. But it is not at 0.457, correct? It's like if you physically see.
Physically see, yes, but actually it's trying to plot these in the matplotlib. These are the numbers it's actually trying to plot. It's just a way when it plots, sometimes it tends to like reduce the number, like 0.47, it might round it up to 0.7 and plot it just because of the space constraint. So you can't exactly pinpoint it when you see it there.
Okay. Yeah. Can you show the for loop, Nisha, you have written?
This one, it's just for loop.
Yeah, copy and kindly put it in the in-call messages.
Box. Yeah, I can.
Thank you. Thank you.
Yeah. Okay. So guys, I think that brings us to the end of Hodgkin-Huxley for now.
Hello.
We'll just take
Madam, can you please explain the threshold portion? Because though the current extends up to 0.7, but the frequency drifts after 4.5, like that.
Yeah, I understand, Arup. You're asking me about this threshold, right? So generally, it's a modeling value which you can keep at whatever you want to. Generally, people tend to keep it around 10 to 20. Below 10 to 20, we don't treat it as an action potential. Maybe it might have that spiking behavior, but it's not exactly an action potential. So it might have counted peaks for that also. So the threshold I have set for my convenience is 10. You can keep some other threshold and check it. It will give you a slightly different number.
Okay, ma'am.
Yeah. Okay.
So I did not understand this question. Can you explain what was the question he asked?
So basically, when you actually see this thing, where did I plot the currents? Just a second. So his question was, see, I can count peaks as any number, right? I can say my threshold beyond 0 is what I count it as peak. Like here, beyond 0, there is a peak. So I count it as an action potential. Or I can set my threshold to be somewhere here, beyond which only I'll count it as a peak. Right? Somewhere like 10, and say I will count that only as peak. So it's a modeling choice which you want to keep. In code, I think I kept it at 10. You can keep it at 0 as well, but generally people tend to keep it at 10 from literature, 10 to 20. It's a coding, I mean, it's your convenience.
Okay, thank you, ma'am.
Yeah. Okay, so guys, it's 3:27 now. Like, let's consider 3:30. We will take a short break for 10 minutes and be back by 3:40. Then we'll quickly do leaky integrate fire and stuff. That won't be this elaborate. We'll just simulate the code for different currents and see how it looks. Is
I
that okay?
have small doubt.
Yeah, Varnika. In meanwhile, others can go for a break. You guys can be back by 3:40. Yes, Varnika, go ahead.
Yes, so in the plotting frequency versus external current section, if I change the iteration, so it changes the
Iter as
plot
is
very,
this iter.
yeah, dt के नीचे जो the variable below dt, iter. I assume that is iteration only.
Yeah.
Yeah, so if I change the iteration to like 1000 or something, the plot drastically changes. So, how does it happen? The concept or the formula is same, but the iteration, changing the iteration, it
Yeah, I'll tell
drastically
you what
changes the plot.
happens. Yeah. So basically, this iter is how much? 1 lakh, right? 1 lakh iterations into 0.01 millisecond, right?
Mm-hmm.
Which is basically 1000 milliseconds, which is basically 1 second, right?
Okay.
When we say frequency, we have to count it for 1 second data. Okay. Now, when you change your iterations, maybe you might have done it for some 1000 iterations. Implies what is happening is you have done it for 1000 times 0.01, which is some 10 milliseconds.
Mm-hmm.
Right. Now, what the code technically does is say if in 10 milliseconds, I only got one peak.
Mm-hmm.
What the code does is now, since I want it for 1 second, that is 1000 milliseconds. For 10 milliseconds, if it's one peak, how much will I have for 1000 milliseconds?
100 peaks. Okay.
Yeah, which is not actually right because you have simulated it for a smaller time, doesn't mean that it has 100 peaks. So that is why we kept it for 1 second at least to simulate, so that my frequency is accurate. Frequency is always computed for 1 second. That is the only way. It's a numerical error if you keep reducing it too much. That's it.
Okay.
Yeah.
Got it.
Ma'am?
Yeah, good. Yeah.
Ma'am, could you tell me some of the projects that may be carried out using this model, ma'am?
So if you ask me about projects, a single neuron can't be of a use like this. What
Yes, ma'am.
people do is they have a network of neurons,
Okay,
and
ma'am.
they'll also tend to model other kind of ion channels, like you can model GABA receptor binding or
Okay.
other kind of channels using equations and create a network or cluster of neurons. Using that, you can explain phenomenon. Like you can
Okay.
explain, say, Parkinsonian phenomenon, how
Okay.
firing takes place under Parkinson's and under normal condition, or
Okay,
under
ma'am.
epileptic condition, how will it vary? But the only consideration is Hodgkin-Huxley is a little intense. That is, it has 4 differential equations. It's computationally expensive. See, for
Okay.
4 differential equations, say it takes some 30 seconds.
Yes,
Now
ma'am.
I have 100 neurons.
Okay,
100
ma'am.
is still a lesser number, but when I
Yes.
simulate, if I'm simulating for 100 neurons,
Okay,
100
ma'am.
into 4 differential equations, it has to solve 400 differential equations at every time. So it's very
Yes.
intensive. That is why we
Okay.
tend to use simple models for designing clusters. So
Yes, ma'am. Thank you. Thank you. Thank you.
yeah. Okay, we'll gather back by 3:40. Hello everyone. I hope you guys are back. Can we start the next part of the session?
Yes.
Good. Thank you so much. So going
Yes, ma'am.
ahead, we would be doing a little simpler neuron models. That is, HH is a very detailed model, right? So we'll be going through the simpler neuron models. Just a pointer to you guys that we might not be doing each and everything as in detail of HH model. So you will be given codes to run the simulations. Right now, there might be a little time limitation because we need to cover 3 models right now. So we'll go a little faster, but you can always stop whenever you have doubts and stuff, or we can discuss it after 4:30 once every simulation is done. Okay. So going ahead, next we'll be having leaky integrate fire neuron. When I say leaky integrate fire, the only change from Hodgkin-Huxley to leaky integrate fire is simplifying it. See, in Hodgkin-Huxley model, the complexity comes because of sodium and potassium channels. Am I right?
Yeah, you get 3.
Yes, this is the time everyone says right. So basically, sodium and potassium channels is the reason why we have the complexity. That is the only reason why we have 4 differential equations. Now, if I want to get rid of it, I'll actually remove both the channels and only have a leaky channel as well as a conductance channel. That is what basically leaky integrate fire neuron is. But again, it can't capture all the dynamics which this neuron model will be done, because of course, I have simplified it too much now. Because if you look at it, it's a 4th order equation, right? Like if you look at the differential equation, it's almost like a 4th order differential equation because of these sodium potassium channels. If I remove it, it completely becomes a 1st order, that is a linear equation. So to bring in non-linearity, we do something called as a resetting step. So if you actually look at the model, this is how it looks like. We only have a leaky conductance, but as you know, in your Hodgkin-Huxley, the entire dynamics are because of sodium potassium. Now I have removed all of them. I need to bring in some non-linearity. So what we do here is, as soon as your voltage reaches certain amount of threshold, it will be reset. It will be reset to certain V reset value. Why do we do it? If I don't do that reset step at all and simulate this differential equation directly, it'll be like a straight line. I don't know how many of you have done electrical and did RC circuits. You'll see a straight line. It won't be reset back, or it won't show that action potential kind of pulses. So that is the reason we reset it. This is a simplification to your Hodgkin-Huxley model, but in a way that you can work around with it. Is that okay? That is how leaky integrate fire works. Why, how this kind of stuff works and all, that actually comes from something called as linear dynamical systems and phase plane analysis, which probably you will be doing in day 3. Right now, I don't want to go through it, but just I'm letting you know that to simplify from there to here, this is what we do. Okay, just remove your sodium potassium channels. Instead of that, I do this hard reset. That is, once it reaches the threshold, I'll reset it to V reset value. Now, there is also an option. When I reset it,
Can I interrupt?
Yeah.
Sorry.
Yes,
The 4th order is on N, but what we are solving for is V, right? It's not a 4th order model on V.
So if you look at the V differential equation,
still a 1st order model. The N power 4 is just, so
Yeah,
N
so-
you consider it as a constant, right?
no, N is a dynamical equation, right? N is a variable.
Okay, fine. Yeah,
So
sorry,
that's
I forgot that. Yeah.
Yeah.
Thank you.
That is the reason I was saying this is more
4th
simpler
order,
one and very linear. Yeah.
Thank you, got it.
Yeah. So when I actually reset it, instead of just resetting it, I can say you stay at that reset value for some refractory period. Any guesses why we tend to do such a thing? It's very manual coding, but why do you think we need such a refractory period?
The neuron takes some time to reset and fire the action potential again.
Yes, so the channels opening and closing takes some time in general, which might be lost when you simplify all of it. So having a refractory period helps you that way, because of such kind of a manual opening and closing, I can't reach beyond certain frequency. But if I keep increasing the current without holding it at a refractory period, it will keep increasing rapidly. That is the reason we tend to do it. Okay. Yeah, so going to the task to be done. Basically, we will be looking at the Leaky Integrate Fire code. Again, in the same code block, you have Leaky Integrate Fire model folder. You can open it. There are two code blocks to it. One is the Gradio version of it, and the other is the normal code version. I'll show both of them and tell you what you can actually play around there as well. I mean, again, it's the same thing. You are going to play around with the currents, nothing more than that.
Ma'am, I have a question. You said that
Yes.
you're removing the potassium and the sodium component in the HH model
Mm.
and you made it a linear model.
Mm.
But you said after that you said something. Can you show that your PPT, PDF, whatever it is?
Yeah, PPT, sorry. Yeah, this one, right? Yeah.
So what did you say? It became a linear equation, and after that you said something. I
So
did not
basically,
get.
when
I
you,
missed.
you basically try to do introduce a non-linearity by actually adding a thresholding. That is, once your voltage reaches certain threshold, I will reset it back to some voltage V reset. That will give you that pulsatile behavior. Otherwise, the alone equation on the top won't give you a pulsatile behavior. Action potential is pulsatile, right? I'll give 1, then 2, then 3. That won't come with the only differential equation. You have to reset it in between to get it back.
Okay, ma'am.
Yeah. So I'll first go through the Leaky Integrate Fire code version of it, and then I'll also simulate the Gradio version and show you guys. Okay. Here also it's pretty much same. The first one is the imports. Let me close some sessions because I have too many sessions. Okay. Yeah, then I actually have a model class where again I have two things. One is your simple function where I'm defining all the variables that is needed. And the other one is a solve function where I'm actually solving your differential equation. So here also, if you look at it, the first one is it just takes in your initial voltage. Then I have an external current. External current can be a step input, however you want to. It's a current value I'm going to give. Then I have how many refractory steps I want to give, which I'm going to give it using your TREF. Okay, then this is where your for loop or your loop for simulating your system runs. Can you identify it? Here is where you have the Euler update, where V at time t is updated using V at time t minus 1 plus dV times dt. And that dV is defined here, which is basically this equation. I know it's very fast to follow up the code like that, but I'm sure you'll have time after the session as well to sit down, look at each of the code blocks. Okay. Now, this is what I meant to reset. When I have certain reset, that is if my voltage is like going beyond certain threshold value, I'll reset it to some EL value, which is my resting voltage. Is that okay?
Yes, ma'am.
Yes, ma'am.
Yeah, so basically this is your code and then you can run the model itself. So in model also you have input current which you can change. Okay, input current you can change it in between like 0 to 15. Say for example, I'm going to give you an input current of 0. What do you think should be an expected behavior? No potential spikes. See, there won't be any potential spike which happens when I give input current to be 0. Similarly, let me try at 1. See, at 1 also it increased the voltage, but it didn't actually reach its threshold voltage, right? Here my threshold is kept to minus 50. So once it reaches minus 50 only, you will have a peak. So then I can have, say, 5. Yeah, now you see. Can you see now the voltage increased till minus 50. Then I reset it back to your previous voltage minus 65. Then again it increases to minus 50. Then you reset it back to minus 65. Can you guys observe that part?
Yes.
Yes.
What did you change?
I just changed the input current here.
Okay.
Yeah.
Okay.
and I'm running without any refractory time. You remember I was mentioning about the refractory time, right? That I can try and hold the potential V reset at certain time point for a certain time. I'm just running it without refractory. I don't know why is this. Okay, let me remove this. Oh shit. I'll remove the title. Yeah. Is that okay, everyone? So what we will do is we'll do a couple of things in this. First, without refractory period, we'll try to run it for different currents. And then with refractory period also, you try to run it for different currents. Can you guys do it yourself for hands-on? You can, if you're not really comfortable with that, then you can also run the Gradio interface, which will create your link and launch it and see. This is how it will show. Just a minute. Yeah, if you open the Gradio link, this is how it will look like. Whoever are using it. If you want to not have the refractory period, just don't tick mark it. If you want to have it, then tick mark it. You can change the input currents here. Just try 0, submit it, it will plot. Similarly, I can try input current of 5, submit it, it will plot. Okay. Then you can also enable refractory period and plot it. I'll give you guys 5 minutes. You can do these stuff. When I say stuff, you just increase your input currents with and without refractory period and try to observe what are the changes you're seeing. Then I'll walk you guys through the results. Is that clear? Anyone has any doubts with respect to what you guys have to observe? Okay, cool. Just try doing the experiments yourself. Maybe in 2-3 minutes, I'll start explaining what is the observed behavior. Guys, once you're done with simple experimentation, can you just respond on chat box as done so that we'll have an idea if you guys have finished it? Great.
Hello.
Yes.
Yes, I wanted to ask one question. Is
Yes.
that why the graph, those spikes that are there in the graph, why it
Huh?
does not look like a typical action
Action
potential? Was it
potential?
because, yeah,
Yeah, so
typical.
so the action potential peak, as you remember, it comes because of sodium and potassium interplay.
Mhm.
Once that is removed, it's not really possible
Mhm.
to have a very similar peak like that. As I said, it's a fourth order equation, it's a linear equation. You can see similar kind of behavior when you at least go to quadratic, which you see next to this. Since it's a linear,
Okay.
it's not really possible. You'll actually see going ahead that you can actually see such kind of a peak if you even use quadratic. That is a second order system.
Okay.
Okay,
So,
maybe, yeah.
yeah, so when we simplify this model, and does it create any difference if someone is doing like their work on this model, or
Uh,
like
so
comparing
it,
to?
yeah, so it depends on what you want to model. If you want to model some kind of a task behavior and stuff, it's okay to use simplified models. But if you want to actually look at the receptor level dynamics, then maybe you have to go for a detailed model. When you do modeling, you have to pick which one is better for your task. See, if I want to model some overall behavior like movement, then maybe a very simplified model, not even this kind of a model, might be needed. But if I actually want to look at a receptor level dynamics, how is it changing? Then maybe I have to go for a Hodgkin-Huxley detailed model. So it depends on which one you have to model. Or maybe I have to define other receptor systems also for that model. So it's a modeling choice you have to make at that point.
Okay, yeah, I got it. Thank you.
Yeah. So guys, whatever I have asked is, I'm going to show it on the simulator itself instead of going through the code. Whichever is comfortable for you guys, you can do that. So I have removed the refractory period for now. I'm going to have very low current, say 0 current, and submit it. You see that there is no input current. So the input current is 0. So the membrane voltage has no change at all. Spike is the time where you have actually reached the threshold. That is where we are assuming that the action potential happened. So spike doesn't show anything right now. Say I increase it to some 5 maybe. Yeah, the input current is now 5, which is a constant input current. Then you can see that the membrane voltage has those spikes. Why do you think that it entered only till -50 and then gotten back to -65? That is because my reset was at -50. You can keep it at higher level also. It's up to you guys. Okay. For this example, I have kept it at that level. Okay. And can you guys see the spike raster? This entire thing, I'm representing it at one point here. That is where your reset and you'll see a spike. Okay. Like at 0.02, you saw one spike. Then around 0.04, you saw one spike. 0.06, you saw one spike. 0.08, you saw one spike. That line indicates a spike happened or an action potential happened. Spike is basically action potential. And such kind of plots where you actually plot spike with respect to time is called as raster plot. It's pretty common across neuroscience community to plot it. Okay. Now, did anyone observe what is the difference between adding and not adding a refractory period? Anyone?
Yeah, there was
Can,
like a step or something.
yeah,
There
there will
was
be a
a
delay,
delay.
right? Yeah. So you see
Yeah.
this plot now, there is no refractory period. Once I add a refractory period, you see this. Can you see that it was held for certain time? I can increase the refractory period also slightly, maybe to 0.05. Then you will see it will be held for a longer time. Okay. So that is the point of refractory period. And if you guys remember in the morning, sir showed some of these kind of plots, right? That when you don't have a refractory period and there is an input current, it will just keep increasing the frequency. But when there is a refractory period, it will saturate to certain frequency. Do you guys remember it? I know he only talked about it very briefly, but it's an actually important phenomenon of neurons. Neurons can't fire beyond a point, as I mentioned before. So we need refractory period in general to be present. Okay. You can actually plot those refractory periods and stuff in your code blocks. If you actually see it, there are code blocks for that. You see it here. Refractory, I can change it to false and plot it. You can see that straight line kind of a behavior where the frequency keeps increasing as you keep increasing the current. But that is not the kind of behavior you guys have actually seen with neurons before, right? Even in Hodgkin-Huxley. But you keep it as true. That is, you add refractory period to it, then it will saturate to some extent. Is that okay for everyone? Yes. So that is your simple leaky integrate fire model. What is the difference? Here, instead of having any fourth order or fourth power systems, I have only made a linear system. What would be the next upgrade to the model? If I want to slightly increase the complexity, what do you think we should be doing after this? Anyone? Make it quadratic instead of linear. I'll make it quadratic, right? That should be the next complexity I can maximum go to. So that is the next model we are going to do. That is basically quadratic integrate fire. Okay. Now, how does quadratic integrate fire works? As I said, dV by dt now will be a differential equation, obviously, but with a quadratic term, that is second order term. That is, there is a v square term to it. Now, this is a general quadratic integrate fire, but we can simplify it. Simplest quadratic equation will be v square plus a or some x square plus b, right? So that is your simplest canonical form. This is generally what is we consider it as quadratic integrate fire model. Even here also, even though there is a quadratic term, even here we need to reset because I'm reducing 4 differential equations to 1 differential equation, which is not a very straightforward thing. So here also we end up resetting it. As soon as it reaches certain peak, we reset it back to certain voltage. Do you guys remember in the morning, sir was showing that for different reset values also you will have different kinds of modifications into the behavior? Do you
Yeah,
remember
yes,
that
ma'am.
parabola plot where he actually showed
Yeah,
it and all?
he
Yeah,
showed 20 variations in this.
yeah, some 2 to 3 variations, right? You can actually try simulating those. Oh, no, that is Izikevich. One more thing with that parabola curve. You remember he showed that parabola and said that there is a
Yeah,
reset to it.
facing,
Yeah,
bursting and stuff.
yeah, no, not facing. Probably, wait, let me show you here. Quadratic. This kind of a plot, if I'm not wrong. He might have shown a parabola and said one side it shows oscillatory behavior and another side it shows some kind of a fixed point behavior.
Yes, sir showed that
Yes.
thing in morning.
Yeah,
he had shown a parabola and he had shown, yes.
something like this he might have shown. Maybe. Where is it? Yeah, something like this he might have
Yeah.
shown, right?
Yeah,
Based on wherever you
Rest.
reset it to, it will either keep oscillating or it will end up going to a rest position, right?
Yeah.
Or you can have a full positive current where it will be like completely reset all the time. Yes. You can actually play around with the code for those things. Maybe I'll go through the code very, very quickly. Will take like only 5 minutes for this, then I'll show Izikevich. Izikevich is very much important in terms of it, so maybe we'll go to that. For this also, we have modeled the equations very similarly. That is, you can see there is a class file for your quadratic integrate fire model. You have an init function where all the parameters come in. Then you also have a solve function where you actually solve it for a specific for loop using Euler equation. Do you guys want me to go through the code again? It's very similar to leaky integrate fire. There's nothing new in it, just that the differential equation is different right now. Is that okay if I skip that part off?
Can you please show the slide where the equation was there?
The simulations part, I'll go back to it. I'll let you guys know what you will actually simulate. Equations you want to see?
The slide 3. Yeah.
The This one?
Yes, yes.
Yeah. Let me know once you're done. Can I move ahead?
Yes, ma'am.
Yeah. Okay. I'm going to just run the Gradio code. Okay. For convenience, you guys also can run the Gradio code itself instead of going through all the code blocks. And open the simulator at your end. Can you guys do that? Just run the Gradio version of the code and open the simulator link. I'll tell you what numbers you can change and actually see. Yeah. Are you guys on the Gradio page or on the simulator page?
Yes, ma'am.
Can you guys? Yeah. All of you, can you guys respond on chat box, or I'll just wait for a minute for you guys? Okay. Cool. Once you have the page, in this you can see these things. Initial voltage, maybe you don't really have to change or play around with it. You have an input current which you can change. Okay. Tau, let it be at its point. We are only going to change two things in this. We are only going to have input current and V reset value. We are going to change and see how the performance looks, or how does it actually change. What are the numbers you're going to change? I'll show you and see the behavior for it. Is that okay? I'll put back the slide so that you can change it. Is it clear? In the simulator, you're going to change the external currents or the V reset value to certain numbers and see the behavior. Is that okay? Cool. So in this, I would like you guys to do two simulations very specifically. In simulation 1, I want you guys to set your V reset value to be less than your square root of minus I currents. And change current value and see how it looks. That is basically keep your V reset as -1. Run it at the current value of -16 and +16. Can you guys do that and tell me what you see? Set your V reset value as -1 and run 2 times, one for current as -16 and one for +16. Once you guys are done, you can write down the observations or unmute yourself and say what is the observation.
How do you arrive at this external voltage to be -16 to +16? Any specific formula is there with respect to V reset millivolts?
You mean current?
Okay, V reset. Yeah.
Yeah. So you remember those parabola, right? That
Yeah.
thing. So I want you to test this behavior here that if I keep my current to be 16.
Okay.
Okay. I mean -16. Then what happens is you'll have roots here at -4 and +4.
Okay.
Right? Now, if I reset it to any number which is like less than 4, this is
Okay.
4, this is -4. If I reset it to number anything less than 4, it will actually show a stable point behavior. If I reset it to any number beyond 4, it will actually show oscillatory behavior. Similarly, when you have a current positive, it will always show that oscillatory behavior. So I want to show those behaviors.
It's coming from V. Okay.
Yeah. So in this one, what I said was just have the reset value to be less than 4, doesn't matter wherever it is. That is -1. I was saying -1, you can keep it at less than any 4 value. You will see that it will show a fixed point behavior for -16 current. And if it's 16 current, since it is up, it will show oscillatory behavior. Did you guys simulate it and see? Okay, so at minus 16, what is the behavior you guys saw?
The voltage trace actually it reached up to it crossed -5 and it became stable.
Yes, so basically there is no action potential kind of a behavior, right? That's basically this condition. That is, it will go here and it will just stabilize to this number. There is no change beyond that. But on the contrary, if you actually increase the number to be like 16, you'll see that it will keep spiking. Is that
Yeah,
okay
that's
for
right.
you guys?
Yeah.
That is basically this behavior. Like when there is no root at all, it will keep oscillating. You'll have more understanding on this, why this behavior arises when you do phase plane analysis. So we're not really poking into why you should see it, but you will actually see it under phase plane analysis. Once you do that, maybe you will have better clarity why this happens. Similarly, if my reset value is something greater than 4, let us set it to some 4.1. Can you then try what is the behavior for different currents? Set your reset to 4.1 and keep it to minus 16 to 16. Did you guys see any behavior? Oh, my end? Yeah, sure, Anup, I'll show it. I'll show both the things here itself. Once everyone runs it, I thought I'll do it. Maybe in a minute I'll change. Yes.
Like, we reset, you asked us to increase more than 4, but when I run it, it is automatically resetting to 0. When I make it 5 and I run with input voltage 16, input current 16, and I submit, I'm getting an output, but here the V reset automatically sets to 0.
Oh, okay.
It is not
One
holding
second.
the number, maybe.
It's not taking the input. Okay, maybe I'll correct that. I think it's no, it is holding now.
Something is hard coded in the code, maybe.
Oh, V reset is coded to be higher number. Okay, can you guys do this quick change? I'll tell you where to change it. In your Gradio code,
Okay.
Go to this line where you have gr.slider value -20, sorry, -100 to 0. Can you increase it to some 20? Sorry, I forgot changing that. And then rerun the code.
Slider, we have value 20. 10.
Yeah, value -20, right? Just change it from -100 to 20. The slide.
Okay.
Yeah, then it will increase the slider value to 20. I think it was set to 0, so that is why it is doing. I'm so sorry for that. Yeah, now it should work. Yeah, so if my V reset is set to 4.1 and my input current is 16, it will show firing. Similarly, at -16 also, it will show firing. Oh, it's resetting back.
Yeah, it's resetting back.
Okay, I'll maybe correct that and send you guys the corrected version of the code. I'm so sorry for that.
No problem. Thank you.
Yeah. So were you guys able to at least understand what might happen there? I'll correct the code and send it to you guys. It's not resetting it well. I'll check what is the problem with it. Yeah. Okay. Then can we move ahead into Izikevich very quickly because that might be useful for projects for certain people at least. Huh? Oh, it's working for you? Okay. Okay, then I don't know what is happening with mine though. Okay, I'll check it anyways. I'll show it properly. But whoever are running the main code can actually change it there if it's not on Gradio. There it will be fine. Okay, should we then go to Izikevich for the last 10 minutes maybe? It would be very quick. We'll only do it on the simulator code so that you don't have to worry about individual codes. Can we go ahead?
Yes, ma'am.
Okay, cool. So Izikevich is also a slightly higher end version of what you have seen as quadratic integrate fire. But the beauty of that model is it can show very different neuronal firings. See, right now you have only seen all the neurons have only two behaviors. Either it doesn't show an action potential or it's a continuous firing. But neural firing is far more different from it and far more complicated. Different neurons show different kinds of firings. Few might show bursting. I don't know if you guys have heard it in the morning properly. A lot of neurons have different kinds of behavior. There can be regular spiking, there can be very fast spiking, or there can be chattering, or also called as bursting, where you see clusters of firing together and then there is no firing. Or intrinsically bursting, that is, first they will burst and then it ends up firing continuously. Such kinds of behaviors are very common across different neuronal models. I mean, across different actual neurons. So Izikevich came up with a model which is a slightly higher complicated model from quadratic integrate fire. In quadratic integrate fire, what we had was we had one differential equation, which is quadratic in nature, and then reset, right? Here in Izikevich, we have two differential equations, one being quadratic with reset points. Is that okay? That is how he increased the complexity, but it is still lesser complex than your Hodgkin-Huxley. That is, in a way, your Hodgkin-Huxley is highly accurate, but it's very expensive. Whereas your integrate fire models are unrealistic, don't you agree? Your leaky integrate fire is not really a very realistic model, but it's computationally efficient, it's very fast. But Izikevich is one kind of a model which provides such kind of a balance. They have this kind of a differential equation. You have two differential equations. If you look at it, first is a quadratic equation, second is a linear one, and then you also have reset. That is how he was actually able to show different kinds of behavior. Is that okay for everyone? Can we
Yes,
go
ma'am.
to the simulator
Yes,
code
ma'am.
then? Can we just directly go to the simulator code then? Yeah, you can open the Gradio version of the code directly and just run it from top to bottom. It will give you your link for simulator. Once let us know on the chat box once you guys are ready with the simulator open. Yes, are you guys ready with the simulator? Thank you, Kumari. Thank you, Angel. Okay, I'm assuming everyone is ready if no one is saying no for it. Okay, cool. So how do we get such kind of different kinds of behaviors across the neurons, or why do we actually tend to see it? See, if you look at the Izikevich model, can you see there are different parameters in it? What parameters can you see on the slide? Can someone pinpoint what are the parameters you see?
V, U, A, E.
V and U are variables. When I mean parameters, they are like constant numbers, which you think are parameters. They are basically A, B, C, D. A, B, C, and D are constant numbers. They are parameters. As I keep changing A, B, C, D, I can see different firing behavior. So if you actually go through the Izikevich paper, he gives something like this. For different values of parameter A and parameter B combination, you can get different kinds of firing. Here RS is regular spiking, IB is intermittent bursting, CH is chattering kind of stuff. Is that okay? So what we are going to actually do in the simulator is, we'll try out doing certain kinds of simulation. Maybe let's just try regular spiking, intermittent bursting, chattering maybe first. Then if time permits and if we have energy, we can look at others. Or you can try out for others. Okay. Maybe I'll explain the simulator very quickly. The same thing is also there in the code, but I'm just showing simulator for simplicity. Okay. In the simulator, if you look at it, you can click on the neuron model and choose different kinds of neuron types. When I choose different neuron types, it basically sets ABCD values at the backend. It will choose certain ABCD combination of values such that it can show that behavior. As you see here, there are different parameter values, right? The same thing is actually there on the code also. If you see it, there are different neuronal models for which we have set ABCD values. These are actually given in the paper itself, who wrote the paper. Okay, say I'm going to set RS. RS here is basically regular spiking. Is that okay? Regular spiking is continuously firing. Okay. Now, once you select RS, there are different current types you can choose. Current can be a constant input or a step input or a pulsatile input or Poisson input or sinusoidal. For regular spiking, you can either choose constant or step. It's up to you guys. If you choose constant I sets the current value. The set value is at 10. You can retain it at that number. Or you can also choose step. It's up to you guys. You can choose constant or step. Others are for different models. Then you just go down and click on submit. Yeah. Are you guys able to get such kind of a plot on your system? I just gave a constant current and selected my neuron model to be RS. So when I give a constant current and set certain values to ABCD, I can actually see a regular spiking. That is, it's a continuous spiking. And you can see whenever that action potential is plotted, I have one spike plotted in that spike times. Basically, this is what is called as raster scans. Raster scan or raster plot is where it indicates a time at which the spike happened. Why do you think it is important? There is a certain part of the community who actually thinks the timing of the spike is very, very important as well. The time at which spike happens also encodes a lot of information in brain. So few people do actually plot spike times to understand that. Is that okay? Yes. You can also try and give a step current also and see if you want for regular spiking. Why am I not able to do this? Can I move this off here? Submit. Yeah, if you actually give a step current, it will give you a step current, and whenever the current is applied, you can see firing present. This is regular spiking. This is our first model that is basically regular spiking. Is that okay for everyone? Okay. Next, can you guys consider fast spiking? Can you guys choose your neuron model to be FS and have same constant current and see what is the difference between regular spiking and fast spiking?
Ma'am,
Yes.
I'm using the code version. So in the code version, there are 4 lines which are commented. Are these those lines where we choose the constant or step current?
Yeah, it's just hand coded there. I think the one which is there is a constant current. You can like remove that line and have the other lines. I think it will give some kind of a step or pulsatile current.
Okay, 0, 10, 0, 10 will be the
Yeah, time at which it is active. So you can check it out. It's up to you. It's a coding thing. You can use that as well. Yeah.
Okay.
Guys, did you guys observe any difference between regular spiking and fast spiking?
Yes, ma'am.
What
The
is it?
frequency is much
Frequency
more
is
high.
more.
Yeah, the frequency
Frequency
is
is more.
pretty high, right? Yes, you guys are right. The frequency should be high. Why is it important? Why do we need two different behaviors? Of course, it's very realistic, right? Because not all neurons fire at the same frequency. Different frequencies will be there for different neurons. So it is important to show such kind of behaviors. Say I have two separate clusters of neurons which have to interact with each other, but one fires at one frequency and the other fires at other frequency, which is a higher frequency. Don't you think this kind of a behavior is very important and one single neuron can explain such a behavior, right? I'm assuming yes. Okay. So that is the difference between your regular spiking as well as your fast spiking. Then can you also guys go ahead and after this choose intermittent bursting or intrinsically bursting in your neuron choice. Keep a step current. That's totally fine. Keep your simple step current or your constant current basically and try to plot intrinsically bursting. So basically you will actually see that there is a quick fast spikes in the beginning and then it actually relaxes very fast. I mean, goes to a normal phasic firing. Can you observe that?
Ma'am, for me, I cannot observe the intrinsically bursting one, ma'am. The amplitude is high, but not the.
Wait, let me see. IB. What is the kind of current you have used?
Constant.
Okay. Right. Then maybe put a step and see. Actually, can you reduce your duration and see? Maybe that would be better for you. If you actually go very close to it and see, you can see it.
How much
Like
should I
when
reduce that?
you have a constant one, right? Maybe keep like 200 or 300 and check it.
Okay.
Oh, wait.
Still bursting is not
Sorry.
happening.
It should be a step input. Sorry. It should be step input. I mean, the current should go from 0 to sudden high. If it's a constant value, it's constant all the time, right? You can't see such a behavior. Can you put it to step? When it's like
Now I can
0,
observe it.
yeah. When there is a sudden change in the current, they will start doing that. You can try even seeing with pulsatile. When you put it to pulsatile, whenever there is a sudden change in the current, you can actually see that. Can you try it out?
Yes, ma'am. That's it.
Yeah, when you give the pulsatile thing, whenever there is a change in the current, you will see that intrinsic bursting. Sorry, it's my bad. Yeah. Is that okay for everyone? Yeah.
Yes, ma'am.
Next,
Yes,
can you
ma'am.
put it as
I
a
have one
step?
question, ma'am.
Yeah.
What is position and sinusoidal current type, ma'am? What does that mean?
Yeah, I'll show that when we go to resonator. Resonator behavior will show you why you need it. Yeah, put your current to your step and try looking at chattering. Chattering is basically bursting. Can you observe it? This kind of behavior is very important when we study Parkinson's. I mean, at least since I work on Parkinson's, I can make this comment that the neuronal behavior from normal regular firing changes to this kind of a spiking behavior under Parkinsonian condition. So it's very important when you're trying to study PD behaviors.
Okay.
Maybe in one of the projects, maybe you will be seeing that in your day 4 or day 5. Any
You
doubts?
asked me to keep it in bursting, no, ma'am?
Yeah, bursting is chattering basically.
CH, you mean?
CH. You can give step or constant current. Step would be fine.
Step, I'm keeping it step.
Yeah.
Hello,
Yes,
ma'am.
ma'am. Yes, ma'am.
Yes.
I think this is
Yes, Abdul.
slightly off topic, but I read somewhere that in Parkinson's, patients don't have brain activity, like the dopamine cells don't produce enough like spikes.
Uh,
That's why they get Parkinson's.
No, so dopaminergic cells die, but because of so dopaminergic cells project to some other structure called as STN
Okay.
and GP. In those regions, you will actually see hyperactivity.
Okay.
Yeah, so they become very bursty and very synchronized firing like this. So they get very overly active there. Cell death at one region causes this. So
Okay. Thank you. Sorry.
Okay. No
It
problem.
changes the direct and indirect pathway, isn't it?
Yeah.
Ma'am, I have one more question,
Yeah.
ma'am.
Go ahead.
So let's say I want to study Purkinje cells, ma'am. What type of model could I use?
I think Purkinje cells also show, cerebellum Purkinje cells also show such kind of cluster bursting, right? Then you can use such kind of spiking networks. Not only Izikevich, there is also one more. So Rose something. There's also another spiking network. Maybe if you can mail us, I'll send you the links of those networks.
Okay, ma'am.
Yeah. So the last one will be resonator. Maybe I'll show this and stop it at that point. By resonance, what do you understand by the term resonance?
Something is in sync with another.
Yeah, so basically, if my input is at certain frequency, my firing also tends to be in that frequency. Say, for example, I'm giving a sinusoidal input for resonator. That is, your neuron type is RZ and the current type is sinusoidal. I think I gave it around 10 hertz frequency. You can plot it and see. Can you see this kind of a behavior? Whenever the current is high, it will spike. Then again, it doesn't. Then again, it spikes. Actually, if you plot the frequency spectrum of both of them will show one frequency high. That is, I of t is at 10 hertz. So your voltage will also show a frequency around 10. Similarly, you can try Poisson also. If you try to give Poisson input, you can actually see whenever there is a current spike, you can actually see that firing happen. So that is a resonator behavior. And that's very important because neurons are not active by themselves. They are activated for some external input. So this will determine that the frequency at which I give an external input determines the frequency at which the neuron should also fire. There are specialized neurons like that. Is that clear till here?
Yes, ma'am.
Do you guys have any doubts?
Ma'am, any example you can give, ma'am, for this one?
I think sounds are always at certain frequency, right? So neurons have to respond to such kind of frequencies.
Okay.
And not only that, if I'm not wrong, some kind of video processing also does this kind of a thing. Certain neurons are active for certain frequency of inputs.
Okay.
Yeah. Okay. Any doubts still here? Okay, so just to wrap up the entire thing, we were able to actually fully do Hodgkin-Huxley. Then I very quickly covered up leaky integrate fire, quadratic integrate fire, and Izikevich. I understand those three are very quick, but you can actually hands-on have the codes with you guys and run it for yourselves and see what is going on with it. Apart from these two models, I think I have also given codes for two other models, Fitzu-Nagumo and Morris-Lakar. They are very much dependent on face plane understanding, but still, if you guys want to, at some point in your life, have a look at those codes, you can have a run through them. Even those codes have a Gradio version of it, so you can play around with it and see how it looks. But yeah, important is Hodgkin-Huxley and the other 2-3 models which we have discussed today. I guess that gives, I know it might be like fully not your coding session, but I'm sure you will try it out yourselves to have a better understanding on how to write the code. If you're here only to understand the neuronal models, then yeah, I think that is more or less covered.
Hello.
Yes.
Yes, ma'am. So my question is quite out of context. Means, is there any kind of research that was conducted so that this kind of neural behavior is applied in artificial neural network neuron?
Yes, you're right. People have seen the so right now there are models like these spiking models, like you have seen that integrate fire model, right? These models, people have tried using it in spiking neural networks and they're able to train it. I don't know if you have heard of SNN Torch, spiking neural network, PyTorch version of it. You can train neural networks on that, but it's not a regular sigmoid neuron or a very general artificial intelligence kind of neurons like sigmoid tanh, but they use spiking neurons here.
Okay.
You can train them. They have come up with certain ways to train it. They actually use the spike encoding. They don't look at the entire trajectory, how the voltage looks. They actually take the spikes itself to train it.
Okay.
Yeah, you can train them. There are also, I mean, you will see in the upcoming sessions. I think tomorrow is more of like neural networks kind of stuff. And the day after tomorrow, you'll see more of oscillator stuff where you will actually see such kind of models more. And how do you train such networks more?
Okay, I see. Thank you.
Thank you. So guys, if that is it for today, yeah, someone else has doubt?
Yes, ma'am. I have one question, ma'am.
Yeah.
Ma'am, these are to understand the axonal propagation of how the ion exchange happens, no, ma'am.
Yeah, in a way, if
Like
there is
the
a
sodium
current that
and
gives to the neuron, how does it actually show an action potential at the end? If you
if
want
I
to
want to,
actually, yeah, go ahead, sorry.
sorry, if I want to study about dendritic like exchange happens there, I think calcium channels may be involved in it. Is it the
Yeah,
same procedure or is it quite different there, ma'am?
it will be very similar. There are also other neuron models which are little more complicated than Hodgkin-Huxley, where they actually model calcium channels also.
Okay.
Yeah, they can actually model calcium channels. You can find it. I don't remember the exact names of them because I work more with abstracted versions, but you can actually find it. People have modeled a lot more neuronal models, even more complicated than Hodgkin-Huxley.
Okay.
Yeah. Shubham, we will try to get it by today night, if I'm not wrong. Yeah. If you guys have no doubts, we can end the session here. We'll be sharing two forms to you guys. One is a quick quiz based on which you will be having attendance because we didn't take attendance other ways. We'll be taking attendance via that quiz itself. And the second is a feedback form. Kindly fill in so that we'll know how to conduct the tomorrow's session. I hope you found the session informative enough. If you guys have any queries, you can always write to us and reach out to us.
Thank you, ma'am. Where will be the form, ma'am?
We'll send it on your WhatsApp group.
Okay.
Yeah.
Excuse
Yeah.
me. Hello.
Yes.
Hi. Thank you for the session. It was really helpful, and I got to know a lot of things. It was very informative as well. I just had a query.
Yeah.
I don't have like very deep background on it, and this might be a very um, dumb question. I don't know. I just wanted to ask that in the Huxley model, we are using the channels like the sodium channels and the potassium channels and all the channels. But when we are moving to other models, we are not using the channels. Like,
Yeah.
I wanted to understand why is that happening and what is the benefit of this.
So basically in Hodgkin-Huxley, the way we use it is by having extra differential equations for sodium and potassium channels. Okay.
Yes.
People have tried to simplify that behavior. See, when you actually look at the closing dynamics of H, it's almost very constant. It doesn't fluctuate more. Instead of having a differential equation for it showing that minor fluctuations, people have simplified it to be a constant number. So that way people have step by step simplified it and got into the simpler models. Now, what is the benefit of it? See, it's always a fight between computational efficiency versus accuracy. The more and more simplified it is, the more and more less biological it might be. But again, if you're not really interested in understanding each and every neuron at synaptic level, rather you want to understand systems at behavioral level, do you really think I might need the Hodgkin-Huxley completely? Not necessarily, right? See, if I want to model a movement-based model, like which can show reaching certain target, where you want to model your hand and model some kind of a reaching, or you want to model some kind of a cognitive task where you're playing a game and how you will play it, that might not need complete Hodgkin-Huxley model, right? Maybe a simple abstracted version will be enough. Like how neural networks work till date. They have abstracted it to the major level, but still they're good enough. So it depends on task where you want to use it.
Okay, got it.
I hope
Thank you
that
so much.
answers your question. Yeah,
Yes, thank you so much.
thank you. Any other doubts, guys? Otherwise, we will end the session here. We'll be sending out the forms in a while. Kindly fill out the forms, both the forms. Okay, I guess there are no more doubts. Okay. Thank you, guys. Thank you so much. We will be
you, ma'am.
meeting tomorrow. We'll be meeting tomorrow at 10 o'clock for your day 2 sessions. Thank
Okay,
you.
ma'am. Thank you. Bye.
Thank you.